Record. Okay. Okay. So good afternoon. First topic in advanced structural analysis is the derivation of stiffness matrix of plane truss. And the two major reference we will be using is the book from Casimali. Oops, pen. Casimali. Casimali. Ano ba yung spelling ko? Check. Okay, tama. Matrix analysis of structures and McGuire. But I'll be only using McGuire for maybe only for this lesson, for the first lesson. Casimali, matrix analysis of structures. Matrix analysis of structures. Okay. For McGuire, matrix, what's the title of that? McGuire, Gallagher, and Zimian. It's matrix structural analysis. Structural analysis. Okay. And remember in finite element class, we were also able to derive the stiffness matrix using formulation in finite element. We have integration of the basic formula. There's B transpose dB and d omega. That's the basic stiffness matrix using finite element formulation. But here we will be deriving the finite element, the stiffness matrix of the truss using basic equilibrium. Okay. So assuming we have this bar, okay, actually loaded bar, and we impose a coordinate system y and x, okay, and the displacement of this bar could be u and v. The displacement along x is u, local displacement, and the displacement along y-axis is v. Okay, but let's consider only the u displacement. Okay, to derive the stiffness, uh, assume a fixed support on both ends, one at a time. Okay, so one at a time. So assuming I will be imposing a fixed connection here on the right end, and then let's impose a unit displacement meaning 1 unit. Okay. Therefore, this node 1 will have displacement delta 1, or u1 is equal to 1, okay, from f1. Okay, therefore by equilibrium we have f2 that will resist f1. Okay, yeah. Maybe I can, there. Okay, oops, admit. Okay, so u1 is equal to f1l over ae. Okay, from basic strength of material formula, right? We are used to know this formula as plane, PL over AE. So in here, let's since we are using F1 and F2, it's F1L over AE. Okay. Now let's rearrange that. So F1 is equal to AE over L U1. Okay. By equilibrium, F2 is negative of F1. Okay. Therefore, F2 is equal to negative AE over L U1. Okay. Agree? Okay. So we're done with the first condition. Next condition is let's assume a fixed support on the other end. Okay. Now F2 will be um, elongating the bar. So we have delta 2 because the deformation is in node 2. Okay. Or designate that as U2, which is 1 unit displacement. Okay. So therefore we have U2 is equal to F2L over AE. Over AE. Okay. Transpose that, rearrange that. F2 is equal to AE over L U2. Again, F2 is negative of F1. So we have AE over L U2. Okay, the negative is here. Okay, negative is there. Negative F1. Okay, that's it. Now let's combine all the terms pertaining to F1 and F2. Okay, so let's zoom in a bit. Okay, F1. I'll use my control one. Where's that? Control one. It's not working. Okay. So what are the terms pertaining to F1? So let's start with U1. I'll use other pen. So F1 is equal to AE over L U1, right? So this will be positive. So that is here. Okay. And how about in terms of U2? F1 is negative AE over L U2, right? So I need to transfer the negative sign there. Okay, so that is this. Okay. Okay, how about F2? F2 is this again. F2 is here. Negative AE over LU1. Negative AE over LU1. Okay. How about here? F2 is positive AE over LU2. Positive AE over LU2. Okay. Now, this from matrix concept, we can transform these two equation in matrix form. So this is it. F1, F2 as a force vector is equal to extract all the common terms AE over L. Then you notice you have unknown U1 and U2 as a column vector here, and positive U1, so that is positive 1, negative U2, that is negative 1, negative U1, negative 1, and positive U2, positive 1. So that's it. So in matrix form, this is our uh, F equals KU. F equals KU in matrix form. Or as I always write, P equals KU. In notation of Casimali, it's P equals ST later on. Okay, so that's it. That's how we derive the stiffness matrix. So if you wanted to know in advance the derivation of this K using finite element formulation, you can where is that? You can check uh, my videos of that here. Where's that? Okay, just this one. this one. Yan. Wala. Yan. Finite element analysis action. Wala dito. I think it's here. Yeah. Okay. So using finite element formulation. By assuming a shape function of, the deformation using two terms polynomial equation a naught plus a1x. Okay, so that's how you do that in finite element formulation. So next is, so that is the local stiffness matrix. Let's now proceed in global stiffness equation or global stiffness matrix. And as you notice, the matrix is symmetrical. Okay? It's a square matrix and symmetrical. Now let's proceed in the global derivation using global stiffness equation. So I already write down the equation in advance because it's too long. So for example, let's assume an arbitrary phi or angle of the actually loaded bar, okay, in space of xy plane. Okay? And again, we have f1 and f2 both ends. Okay, so for node 1, the corresponding displacement or in translation is u1 v1. Okay, u for horizontal, v for vertical. Okay, so I'm sorry, I'm now OC ako sa Zoom Meet nawala. Using it smoothly until now. Biglang nawala. Anyway, then for node 2, u2 v2. Okay, u2 v2. Of course, since f1 and f2 is in has an angle now, we can now find its component. For f2, fx2, fy2. For f1, f1, fx1, fy1. Okay. So the technique here is assume a unit, again, one unit displacement for each degrees of freedom. And because here in global sense, we can have 2 degrees of freedom per node. We can displace laterally, horizontally, and vertically. Okay, translation vertical. Okay, so therefore, we will assume a unit displacement both lateral and vertical. Okay, so for example, for lateral displacement here, okay, so from this original position of the bar, the node 2 displaced laterally 1 unit displacement to 2 prime. Okay, so your total elongation is now delta LU2. Okay, delta LU2. And U2 is 1 unit, of course, since this is theta and this is theta. So delta LU2 is equal to U2 cosine theta or phi. Okay. Okay. Now let's now find out the corresponding equation for that. Where's that? I think this is it. So again, we know delta LU2 is equal to U2 cosine phi. Sorry. Okay. And F2 is equal to AE over L delta LU2. Right? And substitute U2 cosine phi. So AE over L U2 cosine phi. And find out the component fx2 and fy2. So fx2 is f2 cosine phi. Therefore, AE over L u2 cosine times cosine. Cosine square phi. Okay, how about fy2? Fy2 is equal to f2 sine phi. AE over L u2 cosine phi times sine phi. So this one. Okay. Next is fx2, fy2, and we all know for by equilibrium, fx2 is negative of fx1, while fy2 is negative of fy1. Rearrange that, fx1 is equal to negative ae over L u2 cosine square phi, fy1 is equal to negative ae over L u2 cosine phi sine phi. So I made this color magenta to differentiate with other displacement. Now, what if we assume a vertical unit displacement, which is where's the drawing there? Where's the drawing? Vertical unit displacement. Okay, I'll snapshot this one. Okay, it says vertical unit displacement here. Okay, this one. Okay, so if we assume a 1 unit vertical displacement, okay, so our V2 is equal to 1, therefore the total elongation delta L V2 is equal to V2 sine phi. Okay, we already know this from mechanics. So if this is, or by geometry, if this is phi, this is the corresponding phi here. Okay, now let's check the equation again. So delta L V2 is now V2 sine phi. Okay, now F2 is equal to AE over L delta L V2. And substitute this delta LV2. So AE over LV2 sine phi. Okay. So, okay. Then find the component fx2, fy2, the same. F2 cosine phi. Oh, I forgot the phi here. Delete. This should be phi. Yeah. So AE over LV2 sine phi multiplied to cosine phi. So that's it. While F2 sine phi, AE over L V2 sine phi times sine phi, so sine squared phi. Okay. Okay. So to complete the stiffness matrix in a global stiffness equation, you will do the same to the other end. No? So right now, we already assume a 1 unit displacement uh, lateral and 1 unit displacement vertical, V2 and U1. To complete the process, you need to assume another 1 unit horizontal here. This is U1 and 1 unit vertical here. Then this is V1. And assuming this is fixed, right? So what we did is we assumed fixed here. Okay. And laying out all the corresponding equation, you will come up with this global stiffness matrix. Okay. And let's paste that here. And that will be your assignment number one. Yeah. So that is no joking. So so you need to derive the corresponding equation, something like this, but this time you will assume a 1 unit horizontal displacement at node 1 and 1 unit vertical displacement at node 1. Okay, so I enlarge this image. So this is the corresponding global stiffness matrix. Okay, so how do we verify it's true? Okay, okay, so for example, fx1. Let's focus on fx1. Focus on fx1. I want you to expand this raw. Okay, fx1. So fx1 is here. So this is it, fx1, and multiply to this column. So if we expand that, that will be cosine square. I'll no longer write down the full trigonometric function. Cosine square u1 plus sine cosine v1 minus cosine square u2 minus sine cosine v2, right? Which is basically this one. Okay, this is the long form. Cosine square u1 plus sine phi cosine phi b1 minus cosine square phi u2 minus sine phi cosine phi b2. Okay? So that is your fx1. Of course, everything will be multiplied to AE over L. Oops. Which is, where is that? On our derivation, this one. Cosine square phi u2. This one. Cosine square phi u2. Negative, right? Then this one, negative sine phi cosine phi v2 is fx1 here. Sine phi cosine phi v2. Okay? Negative A over L. Negative. Okay? So that means if on your assignment, you will be getting these first two terms. Okay? If you did this uh, assumption. Okay? How about fy1? Okay, fy1. Let's expand fy1. So I'll no longer write down. So fy1 will be equal to sine phi cosine phi u1. Where is fy1? Fy1, where are you? Okay, anyway, let's write down. Okay, so sine phi cosine phi u1 plus sine square phi v1 minus sine phi cosine phi u2 minus sine square phi v2. Okay. And again, where is our fy1? Okay, that's it. Fy1 is equal to u2 cosine phi, sine phi. See? Natakpan. Okay, U2 sine phi, cosine phi, this one. Right? U2 sine phi, cosine phi, negative. Then here, negative V2 sine square phi. V2 sine square phi. Okay? And na-delete. Na-delete pala si FY1. It's there. Okay, FX1 here. FY1, we're done with that. How about FX2? FX2. So this is FX2. Okay. Negative cosine square phi U1. Negative sine phi cosine phi V1. Cosine square phi U2. This is what? Cosine square phi U2. So that is our fx2. Cosine square phi U2. Okay. And sine phi cosine phi V2. Fx2. Okay, this one. This next page here. Yeah. Okay, I'll copy this, and then paste here. There. Yeah. Okay. Fx2 and Fy2. So Fx2, yan, A over L, negative U1, cosine square phi, V1, V1 sine phi cosine phi, V1 sine phi cosine phi, U2 cosine square phi, cosine square phi, V2 sine phi cosine phi, V2 sine phi cosine phi. And which we derived earlier, Fx2 is equal to AE over L, U2 cosine square phi, and according here, AE over L V2 sine phi cosine phi. For Fy2, Fy2, this one, negative sine phi cosine phi, negative sine phi cosine phi, negative sine square phi V1, sine phi cosine phi U2, sine phi cosine phi U2, sine square phi V2, sine square phi V2. Okay? Which we derived here. Okay, Fy2. This one is this one. U2 cosine phi sine phi. And V2 sine square phi. Okay. So this is the corresponding global stiffness matrix of an arbitrarily inclined axially loaded bar. Again, in matrix form, F equals KU. Okay, everything is in matrix form. Okay. Question? Do you have question? Okay, so let's proceed with a problem. So that's why I'm using McGuire as a first method, because as a first reference, because it has solved problems using this simple uh, matrix. Okay, let's pursue our first problem. Okay, this one. So statically indeterminate truss is subjected to the load shown. What are the bar forces and displacement of A? E is 200,000 megapascal. So for sure, this is steel, 200 gigapascal. Okay, statically indeterminate given with the given area and angle of each bar. Okay, so let's use our stiffness matrix. So I'll copy it again our matrix here. Oops. This one, copy, and then paste. Okay, sobrang laki. How do I resize this? Hindi ko siya ma-resize. Laki masyado. Uh, so this is the beauty of stiffness method. You can analyze basically statically indeterminate structure. Okay, unlike the old school approach that you need to use method of sections or so in stiffness method, regardless if it's statically determinate or indeterminate, you can solve the problem. So first, the load is going to the x direction. Therefore, our displacement will be going to the right also. Okay, so for bar AB, so this is our bar AB. We have bar AE, bar AE, AE. We have bar AC also, AC. Ito na lang, AE, then AC. Okay. And last is AD here. AD. Is AD. Okay. Uh, in this method, the beginning and the end of a member is very important. Okay? Because this stiffness method is the beauty of stiffness method is it you can automate this process. That's why in software like STAAD or ETABS, they are using stiffness method. But in again in automation, in programming, you should follow rules. Okay. In remember in our derivation of stiffness matrix, we already impose rule wherein you need to set the beginning node and the end node, right? Okay, like for those using software like STAAD, we need to know the member ends. Okay, so in AB, our beginning node is A. Okay, in AE, our beginning node is A also. In AD, our beginning node is also AD. And in AC, our beginning node is A also. Therefore, the the phi here will be varying depending on the angle of inclination of each bar, right? Okay. Now, in AB, in AB, our restraint is in B, right? I write down this. Okay, AB is the restraint is B. So if looking at our stiffness matrix in AB, okay, for AB, what will be zero there? Is it U1, V1, or U2, V2? Okay, again, looking back, our Derivation here, node 1 is of course U1 for U1 V1. Therefore, in AB, what will be 0 is U2 V2, right? Therefore, U2 V2. So I can set here U1 equals V1. Sorry. Yeah. U2, sorry, and V2 is equal to 0 because B is our end node. Okay. So U2 and V2 will be 0, right? Again, also, the load is to the horizontal. Therefore, there will be no vertical displacement, right? So therefore, V1 is also 0, right? V1 will be also 0 for the first node in AB. Now, using this formula here, what will remain? What do you think will remain? Therefore, what remains will be fx1 because you have unit displacement. Fx1 is equal to only u1 will be available, right? U1 will be available. So, which corresponds to cosine square phi. Okay, so so that will be u1 cosine square phi. So this is our equation for bar AB, right? Cosine square phi. Okay, let's proceed with AE. 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 Our beginning node is again uh, A, while E is the end node. Again, here, U2 equals V2 and V1 is equal to 0. Therefore, in siguro I'll write down here AB. Okay. So this is AB. So therefore, fx1 for AE is equal to U1 cosine square again phi of AE. Here, cosine square phi of AB. Okay? Because we only have one unit. Because we can only have one horizontal displacement at A. Therefore, V1 is equal to 0. Okay? How about AD? AD. Let's proceed with AD. Also in AD, D is restrained, right? D is restrained. So U2 again and V2 again and V1 again is 0. Okay, so our equation will be fx1 again for AD is equal to U1 cosine square phi, because that's only available, phi for AD. Okay, and finally for AC, U2 again, V2 again, and V1 is 0. Therefore, our equation is for fx1 AC is equal to U1 cosine square phi of AC. So that will be our working equation on this problem. Okay. Now, what will be the phi of each bar? If you go, anyway, it's given. Yeah, it's given. So, again, phi for AB is given. Okay. Phi for A is also given. Phi for AD is given. Phi for AC is given. What will be the remaining unknown? Sorry, I forgot AE over L. AE over L. AE over L. Here we have multiplied by AE over L. AE over L. AE over L. Of course, A area is corresponding to their own for each area. Next is substitution of the phi. Okay. Okay. So elasticity is given. Length will be also given because we have given phi and length here, 3 meters. Okay. So what is okay? Substituting those phi. Okay. We have the equation this one. Oops, this one. Okay, given ng phi, no? Cosine 45 square, cosine 315 square, cosine 210 square, and cosine 150 square. Okay, so let's take a look. For AB, it's 45 degree. For AE, it's 315. Why? Because we are referring from the beginning node, remember. So our angle will be from here going there. So 180 minus, I'm sorry, A, sorry, it pertains to AE. Where is AE? AC pala to. Where is AE? This one, AE, 150. Sorry, this is 150. Okay, so this is 150. Okay, for cosine 45, we're done with this. For AC, it's AC is where is AC? This one. AC is 315 because from here going there. So that is 315 because 360 minus 45 degree is 315. Okay. And for AD, where is our D? This one. From here going there. So that is 270 minus, forgot this. Yeah, 30. Oh, sorry, 60. 270 minus 60 is 210. Okay? So agree. And performing the operation, substitute the each area, then the elasticity over the length we have here, you will get these four equations. Okay. Okay. And then by equilibrium, so plot all these forces here. They will be all resisted by 1000 kilonewton as given in the problem. You have 1000 kilonewton. Okay, resisted by the four horizontal forces. So 1000 minus this 270.71 and 2125. You will get UA is equal to 2.55 millimeters. Okay? So using our stiffness matrix. Okay, did you no question? So although it's statical indeterminate, we were able to solve the problem. The Because the unknown is only one. That's the no, that's the catch. Okay, you're able to solve the problem because the unknown is only one. Okay, next problem is Where's the other problem? There's still one more problem. Zoom out, zoom out. This one. Okay. What is the magnitude and direction of the force at point A required to displace that point vertically downward 5 millimeters without any horizontal displacement? Again, E is 200,000 megapascal. Excuse me. So we have two bar, two bars with area 4,000 and area 1,000 millimeters square. And this time, the unknown is the required force at point A required to display this point vertically downward 5 millimeters. Okay. So we have A, B, and AC. A, B, and AC. So this is AB, while this is AC. Okay. So for AB, let's lay down the boundary condition. U1 is 0, right? Because the problem said no horizontal displacement, only vertical, right? So U1 is 0. What else? Also V1 is 0. And also, sorry, U2 rather, because it's restrained on B. Okay, restrained on B, so V2 and U2 is equal to 0. Therefore, V1 is 5 millimeters, right? V1 is equal to 5 millimeters. Yan, as stated in the problem. Now, looking at our stiffness matrix, V1 is available. Okay, V1 is available. V1 here is available. And the rest is 0. So what is correspondent to V1? This one. Sine phi, cosine phi. No, no, no. What is the magnitude and direction of the force P at point A? Yeah, okay. And this one. That. So we will be using these two terms, right? Because U1 is 0, V1 is available, U2 is 0, and V2 is 0. For FY1, because this is node 1, U1 is 0, V1 is available, U2 is 0, and V2 is 0. Okay? So that's why the equation we will be using is sine phi cosine phi V1 and sine square phi V1. As you see here, sine phi cosine phi V1 or VA, sine square phi V1. Okay? That is for AB. Now for AC, okay, lay down the boundary condition. U1 again is 0, V2 is also 0, and U2 is also 0. And V1 here is 5 millimeters. Okay, therefore, same scenario. What we will be using is sine phi, cosine phi, and sine square phi. Where is for AB? Yeah, okay. Okay, so that's why it's general. Okay, so we will be using these two equation. Okay, now Substitute. Phi for AB is simply 45 degrees. So sine 45, cosine 45, and given VA is negative 5 mm, and AE over L is given in the problem. So you will find 176.8 kilonewton. While for FY component, AE over L sine square 45 degree times the required negative 5 mm, negative 176.8. Okay, so we're already computed Fx and Fy for AB. How about for AC? Using the same equation, sine phi, cosine phi, and sine square phi. Again, uh, I just focus on the phi because sometimes students get confused here. Because phi is y153 because AB is, oh sorry, AC is oriented this way. And based on our derivation, we will start from here going there. So that is 153.43 because our angle is 4 over 2. Yeah, 4 over 2. This is 4. Okay, and this is 2. So what angle is that? May calculator kayo, you may compute in advance. So that is shift tangent 2 over 4. That is 26.565 degree. So this is 26.56 degree. So 180 minus the answer is, yeah, 153.43 degrees. So, correct. Okay, so substituting that, 153.43 degrees. And you got this, 178 and 357.8. And uh, by equilibrium, lay the answer here. Yeah. So by equilibrium, combine all those forces. Okay. And we got for PYA negative 355.7, for PXA 181. And that is oriented 26.97 degree. Okay. So that's it. So that's the simplest, the straightforward application of direct stiffness matrix equation. Let's try to solve that in STAAD. STAAD. So that's just to verify that STAAD is also consistent with the stiffness matrix formulation or method. Where's that? Oops, I think I need to sign in first. I'll stop share for a while. Where is that? Okay, signed in na. Configuring. Okay. Takes a while. Okay, by the way, I forgot to introduce SMAT, no? You can also use SMAT. Hey, nagahang. Where is my... I'll paste in the stiffness matrix here. Let's copy this. Copy and then paste. Ayaw. Okay. Okay, so let's say K. Uh, so to introduce a variable, you press in colon, no, not equal. Okay, so where's my on-screen keyboard? Here. Here. Where's that? So K is equal, but I'll need to type in colon. So that will be shift colon. Okay. And since this is a matrix, so type in, sorry, click on matrix here. And it will ask you for the size of the matrix. So this is how many, what's the size? 1, 2, 3, 4. 4 by 4. So that will be 4 by 4. Then insert. And then just type in the corresponding formula here. It's cosine, sine, cosine squared. Okay. So I'll type in cosine. And then, of course, that will be cosine, say, p. I'll let's assign a variable p for the angle. And since that is a square over here, okay. Now take note, remember, take note of the cursor. When you wanted to square this whole function, make sure that the cursor is enclosing the whole name, not the phi only. So I'll press on space. So to enclose that further, so press on space. Okay, as you see, the cursor now is enclosed on the whole function, and then so that will be square, right? So where is the square here? Basically, you can just click this shift 6, shift 6, okay, and then type into, okay, cosine square phi, right? Next, so to move to the other cell or other data, next data, you can just click here, or you can press the arrow. As you see, I'm moving on the other, okay. Next is sine phi cosine phi. So type in sine phi, and then so I'll be multiplying sine phi on cosine phi, right? So I will not directly right away type in asterisk because that stands for multiplication. I need to enclose again the cursor to the whole function. So space, and then shift asterisk, then cosine, then p. Okay. Next is to the next data, negative cosine square phi. So simply I can just copy this. Control C, and then paste here. Control V. Okay. But this time it should be negative, right? Okay, this should be negative. Okay, next is negative sine phi cosine phi. So again, I'll just multiply this. Control C, and then paste here. Control V. Okay, so I'll be moving further here. And since this is a symmetric matrix, right? So we can just copy this. Oops. Control C, Control V, and make this sign. Sign. Okay. What else? Cosine square phi. So copy this. Oops, sorry. Control C, and then Control V. Cosine square phi, sine square phi. Just copy this. Control C, and then Control V. Negative sine phi. Yeah, this should be negative. Copy this here. Negative sine square phi. I'll copy this here. And this is negative. And this one. Okay, that's it. Then copy this. Negative cosine square. negative sine phi cosine phi, negative sine phi cosine phi again, and negative sine square phi. Sine phi cosine phi. Okay, copy this here. So if I have P is say 45 degrees. I can come up again with K. I can now press equal because I'm already finding the answer. Okay, so that's it. But the default of SMAT is radian. It should be radian, I think. What is cosine 45? Then square of that, 0.5. No? So this should be what? 45 times uh, degree. So pi over 180. No? So this should be pi. Where's our pi here? Can I use this? Yeah, all over 180. Okay, so that's it. I need to convert that 45 into radian first. So cosine square 45 is 0.5. So that's how you use SMAT. Okay, and simply just multiply with AE over L. Okay, let's proceed with STAAD. So first, configure the default is should be metric Y up. Okay, because we will be dealing with millimeters or meter, not inch and feet. Y up, that's the default. So I'll explain that later. Why Y up? And then new. Click on new. Better to have your own folder. So select Control V. Then I'll create a folder of STAAD. Then trust. Okay, and then create. Okay, so this is the global axis. Okay, so that's why I'm saying when I'm training in STAAD, as a structural engineer, you should be now familiar with the terminology global and local. And as you see in our derivation of stiffness matrix, we refer first to the local axis, right? And on the second lecture, we now uh, we now define the stiffness matrix of the bar in a global and an arbitrary orientation, assuming it's in a global axis. Okay. Okay. So let's press on 0, enter. That will be our first node. What problem are we going to solve? Let's solve first the first problem. Take this one. Yeah. So let's assume 0 is on A. Now, what will be the coordinate of B here? So since it's 45 degree, that will be, okay, guide me with the coordinates. Okay. So this is 0, 0. Then therefore this is 3, 3, right? 3, 3. Because 45 degree. This one is 3, negative 3. Excuse me. While this one is what? 3. x-axis of this. Okay. So given ang opposite side, 30 degrees. So to get that, 3 over sine 30, right? 3 divided by sine 30. So I'm getting 6. So that should be 6. So 6 and 3. So this should be negative 6 as x and 3 as y. This is negative 6 as x and negative 3 as y. Okay? Okay, because our 0, 0 is here. So, okay, 3, 3, and 6, 3. So, B is 3 and then 3. Okay, so to visualize, let's view on front view. And again, this is our global axis. Ayaw talaga ng zoom in ko. Ayaw lumabas. Na-uninstall yata. Anyway, so front view. Okay, so 3, 3. Next is negative 6 and 3. That will be our node 2. Sorry, node 3. To display the nodes, you press on Shift N. Shift N. Okay, where's our stand? Excuse me. Wala. Shift N. Okay. Next is for the node here. That will be negative 6 again. Oops. And then negative 3. Okay. Finally, positive 6. Sorry. 3 and negative 3. Okay. Then connect them. Okay. So I will now add beam. So click on geometry and add beam. Add beam. So cursor changes. So pick on your nodes. So my starting node is here. Click and then click, click, and then click. So you can now imagine as we draw the beam, STAAD is now getting the stiffness matrix of this later, depending on your start node and end node. Okay. Then press escape. And what else? So let's put the properties. Properties and given is area. So given our area, let's assume since E is 200 gigapascal, which is steel, let's find a corresponding diameter to get this area. For 5,000, uh, 5,000 millimeters square, pi d square over 4. Pi d square over 4. What will be the corresponding diameter? And for 3,000, pi d square over 4. Okay, so 5,000 times 4 divided by pi. Then square root of the answer, I'm getting 79.788 millimeter. So D is 79.78846 millimeters. While here, D is 3,000 times 4 divided by pi, square root of the answer, 61.8. 61.8039 millimeters. Or simply, how many meters? 1, 2, 3, 0.0798. Okay, let's assume 0.0798. So define circle, steel, then 0.0798. Okay, then add. Next is for the other material, 61.8. So 1, 2, 3, 0.0618. So that is 0.0618. Then add, close. Then assign. So my rule here is select the command first, then select the object or the geometry, and then assign. Remember, where is our 5,000? On both the left members. So pick, then pick the two object, then assign. Then pick the command, pick the two object on the right, and then assign. Yes. Okay, what else? We're done with properties. Let's proceed with supports. Supports and then create. Pin, okay, and then add. Okay. Then select the command, select all the location of the supports, and then assign. Okay, what else? Mhm. Okay, and then let's specify this as truss. Okay, beam, specify that as truss because it's an actually loaded, right? So truss, then add. Okay, so command and then select all the object and then assign. Yes. Okay. Then loading. So click on load case, add, then whatever name there because it's only one loading, add and then close. Then put in forces here, click on load case 1 and then add. Then nodal load. That is FX 1000, right? 1000 kilonewton. Going to the X direction, 1000. And then add, close. So select the command and then assign here. But to assign that, you need to have you need to set the cursor nodes. No, right click, select, and then nodes. Okay, then select this and then assign. Make sure assign to selected nodes and then assign. Yes, that's it. And then click on analysis. And then analysis commands. Add, sorry. Then close. And then pick this. Sorry. Then run analysis. Save. Oh, 13 warnings. So what are the warnings? Zero stiffness. Why zero stiffness? Maybe let's
Sir, I think po hindi kasi tayo nag-ano dun sa materials. Kailangan define po natin material muna.
naka-still.
Opo, pero sir, default po kasi yung property ni steel eh. Pinakamaganda po siguro mag-create ng panibagong steel with the same ano po,
Well,
specs.
actually, we will do that later because there will be a discrepancy on the result. For surely. Because we have different elasticity. But for, okay, maybe because, well, when we started the model, we are analyzing in 3D. Okay, so maybe let's try removing, and the problem is stiffness, not material. Okay, so where is our command file? I'll remove truss. I'll remove truss specification because STAAD is analyzing in space. Right? So maybe because I put in truss, okay, maybe there's a confusion of close. Yan. And then analyze, run analysis. Oh, see? So nawala yung warning because when you specify trust, it's like saying that I'm prepared to analyze in 2D, but the first command in STAD is space. So he's expecting 3D forces, 3D displacement, something like that. Okay, so done. Okay, post processing, then apply. So what's our displacement? See? So our displacement is 2.56 mm. Very close to 2.55 mm. Oops, where's that? Yeah, right? Although there's a small discrepancy because default elasticity of steel in STAD is 205 gigapascal, not 200 gigapascal. Still, 0.01 mm, no? Will is very minimal, no? Okay, so 2.55 versus 2.56 mm. Okay, let's try to change that. Yeah, let's do what sir is saying. Let's define a new material. Okay, so create. I'll choose steel as a default, but use steel new. Then see the default is 205, so it should be 200. And then okay, then yes. Mm, yeah, steel new, and then select assign. Okay, yes. Let's check if consistent with the properties. Okay, not consistent. So still new. Then assign, close. And then assign. Okay, that's it. And then analyze again. Okay, no warning and then done. Post processing. Okay. Lumaki pa nga, no? So 0.62, 0.63 mm. Anyway, no? So, so as you see, there that could be, they call that mathematical, rounding off na lang. Okay? So see, so it shows that you can analyze the problem using stat also. Okay? And then if you want to exaggerate the displacement, so just press on control and then yung wheel button of the mouse. Okay? So it's going to the right, of course. Okay? So that's it. And as you notice, there's a warning because there's an inconsistency earlier because the script is running on space and yet I impose a trust. So that is most likely the cause. Okay? When you define a trust, the command the software is ready to analyze only in 2D, but it detects that you are modeling in 3D. Okay. So that's it. Do you have questions? And I might upload a lecture uh, in Trust again, maybe for other problems. Okay, at least I was able to show you the verifying the problem, the textbook problem in STAAD, and how to analyze STAAD and manually solving that here. Okay, so that means although there's a statically indeterminate problem, you can solve it manually as long as the unknown is limited to the number of equations that you can solve in calculator. In fact, if I can, you can also solve manually if the unknown is 3, right? Because your calculator can solve 3 by 3 matrix, something like that. Okay. But more than 3 unknowns, you will need Excel spreadsheet at least, or SMAT. Okay. So, uh, do you have questions here? Next will be more on the another derivation of stiffness matrix, but Casimali's approach. Not entirely Casimali, but using referring to Casimali. Okay, so for now, at least you learn how to apply the stiffness matrix in solve problem. Okay, so that's it. Okay, so we can now end the lecture for now.
Sir, upload naman po yung lecture today pa.